Next exercise 17. We have an arbitrary group here G in which we have these expressions. We need to simplify them as far as possible so that the end result has no brackets, and these symbols A, B, C, these are group elements in this arbitrary group G. In this simplification, we are of course going to use the few properties that we have in this section. Although we are not going to explicitly mention them at each step where they are being used, we will just simply mention them verbally, not in writing. So the first one can be simplified like this. We have ACB, CBAB whole inverse. Now this is equal to, now I think it will be better to write it as an equation array. In that format it will look better. CBAB whole inverse. First of all, because of the general associative law, which precisely is which one is it? Theorem 3.3. This bracket is not needed. So we can just simply write ACB and then this element, which is the inverse of something. Here, however, we of course need the brackets. Now, by that same associative law, this product inside CBAB can be thought of as the product of CB and AB. So these two elements are equal, this product and this product, so their inverses are also equal. Now you use that result which tells you how to take the inverse of a product. The inverse of a product is equal to the product of the inverses of the individual elements, but the order is reversed, and that you find here in theorem 3.4 part 2. So using that we get AB inverse, CB inverse. Again you use that and you get this thing ACB. Here also when we take the inverse of AB, that is the product of the inverses of A and B, but in the opposite order, I mean in the when you switch the things. So you get B inverse, A inverse. This inverse is this, like that. This inverse is B inverse, C inverse. If you want, you can mention alongside these steps exactly what theorem you are using, but since the use is obvious, I have decided not to write them. Now again, using our general associative law, these brackets can be removed. A inverse, B inverse, C inverse. So you see that B inverse gives us the identity element, whatever it is in that group. C inverse, and the identity will vanish. For example, you can think of this as the product of ACE and the rest of the things. So in that ACE, that AC times E is AC by the definition of the identity element. So ultimately we have AC A inverse, B inverse, C inverse. Now just to make sure that what I have done is correct, let me just go through the calculation once more. ACB, so here B inverse, A inverse, B inverse, C inverse, and these two things cancel out, so we are left with AC A inverse, B inverse, C inverse. Looking at these two steps, I mean this step and this step, you notice something, that whatever we have in that result, which asks us to take inverses of the individual factors but reversing the order, that in general is true irrespective of the number of factors we have. What I am trying to say here is that here you have CBAB whole inverse. So just like this result for only two factors, you have a similar result for any number of factors. This inverse also is the product of the inverses of these individual things, but you have to write the exact opposite order. Instead of starting from C, you start from B. So this inverse would be B inverse, A inverse, B inverse, C inverse. You see here B inverse, A inverse, B inverse, C inverse. Okay, and that in general is true. In fact, that you can prove by induction on the number of factors. That is, what I am saying is that this result, that AB whole inverse is B inverse, A inverse, can be generalized like this. Say you have any n number of group elements, you take their product and take the inverse of the product, where n is some positive integer, any positive integer, then this is equal to this. And this can be proved by induction on n. And this is as far as we can go. This is the most we can simplify if our group is an arbitrary group. And here we are given an arbitrary group without any further restriction on the group. So this is the first one. Now like that, we calculate the second one. In the second one, now this time we are not going to do this much calculation. We will directly use that observation which we have seen here to write the inverse of this A inverse BC A whole inverse. So this will be, we start from here, A inverse, then C inverse, then B inverse, and then the inverse of A inverse. And this, of course, you cannot actually do anything else with these first three factors. But this fourth one equals A, and this is your part 1 of theorem 3.4. So that's just it. This is the most you can simplify in this situation. And the next exercise is also similar, But similar means exactly we have the same expressions, but now instead of an absolutely arbitrary group G, we are given additionally that G is abelian. So this is the 318. Repeat the preceding exercise assuming G is abelian. Now this extra hypothesis that G is abelian allows us further simplification. We can, okay, so what do we have to do here? We have to simplify those same expressions. Since we already have got this much, so we start from here, start from where we left off in the previous exercise. A, C, B, C, A, oh sorry, not C, A, C, B, A, B, whole inverse. We have found that this equals AC, A inverse, B inverse, C inverse. Now because G is abelian, using the fact that the operation on G is commutative and using the fact that the operation is associative, it's always associative in any group, many times as we want, we can after some steps have this product like this, written like this: A inverse, C inverse, A inverse, C inverse, B inverse, which is E B inverse, and that is equal to B inverse. So this further simplification has been possible because G is abelian. Just like that, in the second part, we have A inverse B C A whole inverse equal to A inverse C inverse B inverse A, which can be written as A inverse A. If you want, you can change the order, if for no reason, just simply because alphabetically B comes before C. E B inverse C inverse. So this is B inverse C inverse. Since we don't know any further relationship between B and C, so we can do just this much. And the next one, we again have like the previous Lee video, group table, one particular group table. Fill in the rest of table 3, 3. So it's already there in the text. So let's first draw the table that is already given. There is some group in which 4 elements are there, and we need to make the table accordingly. Some entries are given in the table, but some have been left, some cells have been left vacant. We need to fill them in. So what already are given are these. These are the elements A, B, C, D. So the given ones are D, then B, then B. Not many elements are given. Most of the cells are vacant. A and A. Now to completely fill out the table, we go just like we went in the previous, in the previous video. Let us recall that we discussed about a property of group tables, that they are magic squares. Every element of the group appears in every row and every column exactly once. And we also know, we have already discussed it, why this happens. This happens because of the cancellation laws. So I am not going into that once more. So we use this property to fill the thing out. First of all, so whatever we have to put here are just these 4 symbols, A, B, C and D. So in the first row, we see that we already have B and D. So that means A and C need to appear in these 2 columns, in these 2 cells. So A and C need to appear in these 2 cells. So let us look at this cell. This cell will either have A or C. However, it cannot actually have A, because then this 4th column would have 2 A's. That is not permitted. So it must have C. There is no other choice. Now because the first row must have A, so this one must be A. Okay. Next, Like that we have to think. Next, let us think of completing this, say the second column. In the second column, we already have A and B, so that means we now need to put C and D. So this cell, for example, can have either C or D, but we cannot just simply decide from what we see here whether it will be C or D. That cannot be decided yet. Just like that, here also we really don't know which one of C or D will appear. So that means these cells will have to wait. Okay. What about these cells? Yeah, here I think we can decide. See, A and C have already appeared in this column. So that means we are left to put B and D. Now because B has already appeared in this row, we cannot have another B here. So that means this one has to be D. And that just means this must be B. Now can we decide which one of C or D will appear here? Still we need more information. Okay, let us try this one then. This second row. B and D already are there. So that means here either we will have A or C. That we cannot decide yet. Here also we will have either A or C, but we cannot have C. We cannot have A because we already have A in this column. So this must be C. And that is why this must be A. Okay. Next, since in this column, the third column, what do we need to put? D. So this must be D. Right. So now in the third row we have A and D. So this one is either B or C, but it cannot be B because B is already here in this column. So this must be C, and hence this must be B. So now looking at the first and second column, A, B, D, so this has to be C. A, B, C, so this has to be D. So this is the completed group table for that group. Like that, we have another group table in the next one, but of a different group. Let G equal to, okay, but before I leave this solution, let me just see if I have got the correct one. D, A, B, C, right? A, B, C, D, A, B, C, D, B, C, D, A, B, C, D, A, and C, D, A, B. Yes. G, Phi, W, X, Y, Z, Phi, W, X, Y, Z. Be a group with 5 elements. Further, suppose that PW is equal to Y, Phy is equal to Phi. Some of the combinations are given, some of the operations are given. and some are not given. Note one thing, that you cannot just simply make this table and keep the solution like this. You need to write all these steps, and if you want to rewind the video a little and go back to the procedure of exactly how we found these elements. You mentioned that because of the cancellation law, each and every element of the group will appear in each and in each row and each column exactly once. So that is why from what we already have in the table, we proceed like this, that first we, because of these things, this cell must have this element. You need to write those things, otherwise this just does not convey any information. It is the completed thing. So you need to write how we ultimately found this. Next, Wx is Z, Xv is W, and ZW is V. Filled in the group table for G. So let us first make the table, and first let's just write the fill in those cells that are already given. So how many are there? 5. So we need 6 rows and 6 columns. V, W, X, Y, Z. V, W, X, Y, Z. So we are given that VW is Y, VW is Y, then VY is V, VY is V, okay. WX is Z, XV is W, oh here itself, and ZW is V. Oh, so this row is not given, nothing is given in this row. So let us start our process. Now here you can actually speed up the process by observing something. Note that because we are in a group, so one of these elements is, it must be the identity element. Now can we figure out which one it is from what we are given? In fact we can. You note that it's given that Vy is V. So let me write the thing here. Since Vy is equal to V and V can be written as V times identity, where E is the identity in this group. Whatever it ultimately turns out to be, there is one identity we know, and we also know that any element is that element times that identity. We get by the cancellation law you can so cancel V from both sides and obtain this thing Y equal to identity. Now because Y has turned out to be the identity, Y will behave like the identity. So no matter what you multiply with Y, multiply means what you operate with Y, you will get that thing itself. So for example, Vy is V, that is already given. Wy will be W, Xy will be X, Yy of course will be Y, and Zy will be Z. Just like that, there will be a row. The row for Y will have all these elements. Yv is V, like that. Yw is W, Yx is X, Yy is Y, Yz is Z. So you can see that what we were thinking is a very big gap. Actually already it has been filled. Now we can proceed. Now we know many elements. Okay. So we have one complete row, one complete column. Right. So now what can we do? Let me just for once see what I have done here. Which one is the first one that I was able to decide? It is this one. So in this second column, we already have three elements, Y, W and V. Y, W and V. So that means X and Z now need to find their proper places. So what will this be? This cannot be X because we already have one X here in this row. So this has to be Z. And that is why this has to be X. Next we can look at this row. For example, here also we don't have two cells. We have two cells vacant, X, Z and W. So Y and V need to be put now. This one here we will have either Y or V. However, this column is not helping us. Here also we will have either Y or V, but we cannot decide yet. Okay. What about the other cells? What about this one? Here we will have either Y or V. Oh, but we cannot have V because we already have one V here. So that means this has to be Y, and that is why this has to be V. Now can we decide what this one will be? W, Z and X. So that means this is either Y or V, but it cannot be V. So this has to be Y, and the other one will be V. Okay. What else? X, V, Z. That means Y and W. This one, it cannot be Y because we already have Y here. It has to be W. So the other one has to be Y. Fine. So 4 more are left. Y, W, V. So that means either X or Z, which we cannot decide yet. What about this one? Oh, here also we will have either X or Z, but we cannot have Z because we already have that here. So this will be X and hence this will be Z. Now the other two will automatically come out. Z, Y. So that means this will be X. X, V, Y, Z. So this is W. Now let me check. Z, Y, W, V, X. Z, Y, W, V, X. Y, X, Z, W, V. Y, X, Z, W, V. Okay. W, Z, V, X, Y. W, Z, V, X, Y. V, W, X, Y, Z. V, W, X, Y, Z. X, V, Y, Z, W. X, V, Y, Z, W. Yes. So this is the this thing, of course, I did not want to write it here, make it look bad, but this you need to write before the table, because of this only you have been able to immediately fill in this row and this column. So you need to write it on top of the table. So here the solution ends. Next. Show that the following are equivalent for a group G. Two statements are given. The first one is this: for every elements A, B and C in G satisfying this equation, AB equal to CA, we have B equal to C and number 2, the second statement is this: G is abelian. So the first statement is a sort of cancellation law. It's not quite the cancellation laws that we have. It cancels A from both sides of this equation, but note that here A appears to the left of B, here A appears to the right of C. So this is neither the left cancellation law nor the right cancellation law. It's a different kind of cancellation law on its own. So what we have to show is that if in our group this is true, then our group is abelian, and the converse. If in an abelian group, this will be true. So the converse is easier to show, so we show that first. Let us first prove that the first statement is a consequence of the second one. Let G be abelian for any three elements let AB be equal to CA. Then AB is equal to AC using the fact that, using the hypothesis that G is abelian. So now we can apply the cancellation law that we have in our G. It's precisely the left cancellation law. We can now cancel A from both sides, giving us B equal to C. And which is just the first statement. So by the cancellation law or cancellation laws, I'm not exactly sure what the author is calling these laws. If you want to be more specific, you can mention the part of the theorem 3.5 that is being used here. B is equal to C. So 2 implies 1. Next, we prove this. So let G be a group in which statement 1 is true. There is no need to write all these things because it's already there and it has a name, statement 1. So let G be a group in which these things are true. Now we need to prove that G is abelian. Let A and B be any two elements in G, which are not necessarily distinct. They may be the same thing also. We don't know. Now we need to prove that AB is equal to BA. Note that AB is equal to, we need to write something times A. So what is that something? Which is anyway true in any group G. A inverse BA. Okay, how about this? AB A inverse A. Then A inverse and A will give us E, which will with AB, that will it will give us AB. Now look at this. It is like this equation, AB equal to CA. In place of C we have AB A inverse. So our first statement says that in this case B must be equal to this C. So we must have B equal to AB A inverse. Hence, but then what will happen to AB? AB will then be, oh no, okay, instead of starting with A, we can start with AB if we want, but let's just start with BA. It's easier that way. Then BA is, because our B has been shown with this, A, and this now equals A inverse and A, they vanish and we are left with AB. So we have been able to show that BA is equal to AB and hence G is abelian. This proves, or this shows, that G is abelian. So 1 also implies 2, that is the two statements are logically equivalent. And there is one more. Suppose that in the definition of a group we replace the third part with the following weaker condition. Third part or third axiom. Third part he has written, okay. So the third one is existence of identity. In its place, we are going to assume a sort of existence of a partial or one-sided identity. So we call it 3 prime, the alternative third condition. There exists an element E belonging to G such that for every element A in G, AE is equal to A, and that's it. We are not saying also that EA is equal to A. So you can, in this sense, you can call this E not just an identity, but it's only a right identity. It behaves like an identity by being on the right side of the element. When you multiply any element, when you operate on any element by E from the right side, then it behaves like an identity. We don't know whether this is also A, and that's what the author is also saying. That is, we do not insist that EA is equal to A. Show that with this modified definition, we still get a group. That means everything else about the definition is like before. Only in this existence of identity we have this alternative, somewhat weaker existence, that we only need a right identity. Now we need to show that such a right identity would also be a left identity, because then we have our original definition back and it will then be a group. So we need to show that EA is also equal to A. So let A be any element in G. To emphasize the arbitrary nature of A, if you want, you can also write like this: let A belonging to G be any element, then we have, so we need to figure out what EA is. So let us start a series of equations which go like this: EA is equal to EA, EAE. Why? Because E acts as a right identity. In place of A we can have EA, so EAE will be equal to EA. Now in place of this E we can write EA. In place of this E we can write A inverse, A inverse, inverse. Because all the other axioms are like before, so the fourth axiom is like before. every element has its inverse. So A has its inverse, which is A inverse, and A inverse being an element in G also has its own inverse, which is A inverse inverse. But there is one, there is a potential for making a very tremendous mistake here. Don't write A in place of A inverse inverse. Do you see why? That is because where are these inverses coming from? From the fourth axiom. But don't forget that the system now we have actually is not a group, not yet. In fact, that's what we are being asked to show. So all these results that you have in this section about groups, none of them is available to you, because this is who knows, if it may not be a group. We are trying to show that it is a group. So you cannot use any group theory result here. You are only allowed to use the axioms. And here we have used the axiom, the fourth axiom. Here also in this step we have just used this new third axiom. So all the things now must be carefully dealt with. One more thing is that write the brackets properly, because since this is not yet known to be a group and we are in fact trying to show that, the general associative law is also not available. The actual associative law, the second axiom, is there, however, and that's what we are now going to use. EA, so this is equal to EA, A inverse, A inverse inverse. In order to be sure that whatever you are doing is logical, you can write alongside these steps exactly what you are doing. Okay, in fact I suggest you do that. Again, using the axiom, you don't have to write much. You just write by axiom here, for example, by axiom 4, here by axiom 3 prime, here again by axiom 2, and here again once more by axiom 2 you have this. Again by axiom 4 this, and EE is E, and this comes from axiom 3 prime. Anything that has to do with E comes from axiom 3 prime. So this E is not our ordinary inverse, ordinary identity. E is only a right identity. But anyway, this you can carry on with this calculation further like this. This E then again by axiom 4 can be written like this: A inverse, and along with that we have inverse of the inverse of A. Again use the associative law axiom 2 to write this. So far everything is logical. Now this is E, and AE by axiom, this one is E, and AE by axiom 3 prime, the new axiom, is A. So we have in fact shown that EA is also equal to A. So the new weaker axiom 3 prime actually implies the stronger axiom 3, and hence the system you have from this somewhat watered down or weaker version of the original group definition actually gives you again a group. Now there is one more thing that I must mention. I am saying that all the axioms except the third one, they are same. That is not actually true. Note that the fourth axiom, which says that if you have any element in the group, then there exists an element B in the group such that AB is equal to BA is equal to E, and this is their existence of inverse. And this B you ordinarily denote using this notation A inverse, because you have E in the fourth axiom. The fourth axiom now is actually not the original fourth axiom. This E that you see here is actually this right identity E. Everything else is same, but the entity E you see here is actually the right identity. So technically speaking, this is also a new axiom, although nothing much has changed in the structure of the things that we have here. The only thing is that the nature of this identity is not exactly like the previous one. But now, of course, after proving all these things, we have seen that this right identity in fact is the two-sided identity. So this is just simply an observation. It has no visible effect in these calculations. So E acts as an ordinary identity element in G. Thus, the system, I am saying G. Do we really have any? Yeah, we do have G here. The system obtained by replacing the third axiom with the weaker 3 prime is in fact a group this completes the solution. And along this same line of thinking, actually one can relax or make the fourth axiom also weaker, just like this, and that corresponding system will also be a group. Namely, in the fourth axiom, you just demand that there is a B such that AB is E. No need to demand also additionally that BA is also E, because one can prove that with only, now this just like that right identity thing, just like how we decided to call E in this context, you can call this B a right inverse of A. So what I am saying here is that you can give a much bigger definition of a system where you have a set G, a binary operation on G, such that G is closed. Saying that there is a binary operation on G automatically means that G is closed with respect to that binary operation, and that operation is associative, and there is a right identity element, and every element has a right inverse. If this is your new definition of a system, that can also be shown to be a group, which however we are not doing here. We have only shown that existence of a right identity is enough. So now if you are given some system which you need to show is a group under some operation, you know that it's enough to find an element E which behaves like this for every element A in G. Then this element E will automatically also behave like this. There is no need to additionally verify this. It is automatic. And that concludes this set of exercises. In the next Lee video, we will solve further exercises. So this ends the video here. If you have any doubt or any queries, you can write in the comment section below, or you can mail me at my usual address. It will be there in the description. And tomorrow is Sunday, so tomorrow we have our analysis. And just to repeat the thing which some of you may not know, on Saturdays we have Gaussian solutions and Lie solutions alternatively. For example, this Saturday we have gone through Lie, so next Saturday it will be Gaussian, and then again Lie, again Gaussian. It goes like that. So with that, I sign off. So see you tomorrow with analysis on a mathematical room. Until then, this is me, Lucifer. Have a nice night.